All right, folks, in this video, we're going to talk about piecewise functions, which is an old and familiar topic, and finding limits, which is also an old and familiar topic. So we are really not going to do a whole lot brand new in this video. We're simply going to meld or merge two old ideas together. All right, so just as a reminder, a piecewise function is so called because it comes to us in pieces. So if we jump right into number 1 here, it says graph the function f of x, which comes to us in two parts. For the x values that are greater than or equal to 1, we are going to use 3x minus 4 to evaluate. For the x values that are less than 1, we're going to use the expression x squared plus 2 to evaluate. So in order to graph this, to go build my table, I'm going to use one table for x values greater than or equal to 1. I'm going to build a second table for x values less than 1. I'm going to start my table at 1. Notice, regardless whether this says greater than or equal to or less than or equal to, I'm going to include a 1 in both tables. The difference is for the greater than or equal to, I'm going to use a filled in circle in my graph, whereas the strictly less than, I'm going to use the open circle. So again, the expression that I'm using here for the x values greater than or equal to 1 is I'm using 3x minus 4. So I'm just going to go do some mental math here. I think this is negative 1. 3 times 2 is 6 minus 4. And I'm going to stop calculating out loud because that'll be super annoying for you. And then I'm going to go plug into x squared plus 2. And now I'm going to go graph my function with its two pieces or two parts. Perfect. So note my arrows at the ends of the graph to indicate that goes on forever and ever. It doesn't end. Now I can go ahead and use my graph to evaluate my limits, and I'm doing exactly the same thing that I did yesterday now. As we approach 1 from the left, it looks like the y values are headed towards 3. As we approach 1 from the right, it looks like the y values are headed towards negative 1. That means the value, or sorry, the limit for our function is x approaches 1 is a DNE or does not exist. The right end behavior as we approach infinity, the y values also approach infinity. Left end behavior as the x values go towards infinity, the y values also continue to head up. And the value of our function at 1, well, we've got this point 1, negative 1 that's on our graph. So an input x value of 1 is going to generate an output or a y value of negative 1, making the value of f of 1 equal to negative 1. All right, so there is my first piecewise function. I think for the second one, what I'm going to have you do is pause the video, and I'm going to have you go Generate values for the first part of the domain, less x values less than 0. For the second part of the domain, x values greater than 0. And then go draw your graph. So go ahead, fill out your table of values, draw your graph, and once you've done those things, then you can resume the video to make sure that your graph is correct before going to evaluate your limits. All right, so take a minute, pause the video, make sure your tables look like mine, make sure your graphs look like mine. And now that we're on the same page, let's go find some limits. So as we approach 0 from the left, I'm going to hop on that function and head towards 0 from the left. My y values are cruising towards -4. As we approach 0 from the right, I'm going to hop on that function and head towards 0. And as I get closer and closer to 0, my y values are headed towards 5. I have different limits for 0 from the left and the right, meaning that the limit as my function f of x approaches 0 is a dne. As far as the end behavior, the right end behavior towards infinity, well, the graph is headed down, so that's going to be a negative infinity. Left end behavior is my x values become more and more negative, my y values become more and more positive. And lastly, f of 0, well, the point 0.05 is on my graph. So an input of 0 for x will yield an output of 5 for y, making the value of f of 0 equal to 5. All right. I wanted to head to next page 11. And I think I'm going to make a change and instead head towards page 9, because on page 9 I want to review the graphs of the rational functions. So we haven't looked at anything like page 9 since the fall, so this is a change from your calendar. We're actually going to go ahead and we're going to graph the rational function on page 9. So to start this out, I'm going to remind you that in order to graph a rational function, we want to find all of the attributes and characteristics, including the x-intercept, the y-intercept, any asymptotes. So looking here, first thing I'm going to do is look for a point of discontinuity or a hole. And I would look for a point of discontinuity or a hole by canceling out common factors from the numerator and denominator. So I'm going to go ahead and down here where I've got a little room in the bottom right hand corner, I'm going to factor out a 2 from each of the terms in the numerator. I'm going to go ahead and factor the denominator. The denominator will factor into x minus 4 times x plus 1. The common factor of x plus 1 will factor from both my numerator and denominator, making the x value of my point of discontinuity, or the x value of my hole, equal to x equals -1. And that x value comes from that factor that was canceled from both the numerator and denominator. So my simplified function now is 2 over x minus 4. And to find the y value of my hole, I'm simply going to plug in that x value of -1. So -1, -2/5 is my whole or my point of discontinuity. I'm going to go ahead and plot that because if I don't, I always tend to forget it. So there's a nice little hole there. Uh-oh. Something is happening here. Phew, thought I lost everything for a minute there. Okay, x-intercept. Just in case you have forgotten, we are going to find the x-intercept by setting the numerator equal to 0. And I'm going to perform all these on my simplified function. So on my f of x equals 2 over x minus 4. So when I set the numerator equal to 0, 2 equals 0, that can't happen. That tells me that there is no x-intercept. My y-intercept, I'm going to find by setting the x value equal to 0. So to find my y-intercept, I would go set my x equal to 0. So my y-intercept is at 0, -1/2. I don't care if you find all of these and then go graph them, or find them all, then graph them all. Your choice. It really doesn't make a difference. The vertical asymptote we're going to find by setting the denominator equal to 0. So x minus 4 is equal to 0. That tells me that the vertical asymptote is at x equals 4. I like red for my asymptotes. Remember that asymptotes are always dotted. And remember that a graph will never, ever, ever cross a vertical asymptote. A horizontal asymptote I'm going to find by comparing the degrees. In this case, my simplified function is bottom heavy because the degree of 1 in the denominator is greater than the degree of 0 in the numerator. So this guy is bottom heavy, and whenever you have a function that's bottom heavy, you have a vertical asymptote at y equals 0. So I'm going to go ahead and graph that asymptote as well. And a slant asymptote, there will only be a slant asymptote when you're top heavy by 1, because there is already a horizontal asymptote. We were already bottom heavy. That means there is no slant asymptote. All right, as far as to kind of fill in the blanks here, I'm going to think about this graph as having two pieces or two sections, one to the left of x equals 4 and one to the right of that asymptote x equals 4. To the left, our graph is going to look like this because remember, in behavior, it will follow the asymptote. And again, we can never, ever, ever cross a vertical asymptote. You can cross a horizontal asymptote at a hole or at an x-intercept. We don't have any x-intercept. And the only hole that we had was at 0, -1/2, not on that horizontal asymptote. So we know that our graph, in this case, will not cross that horizontal asymptote. So there's what our graph looks like to the left of x equals 4. To the right of x equals 4, one of two things is going to happen. It's either going to look like that, entirely above the horizontal asymptote, or it's going to look like that, below the horizontal asymptote. To figure out which one of those it's going to be, I'm going to evaluate the graph or evaluate the function for some number to the right of 4 or bigger than 4. Because I'm not working with a calculator, I'm going to go for an x value of 5. So I've got 2 over 5 minus 4, or 2 over 1, or 2. So the point 0.52 is on my graph, and that tells me that to the right of 4, the entire graph is going to lie above that asymptote. All right, so there is my rational function. You've got a nice little repeat course in rational functions. Now I can go ahead and evaluate my limits. As the graph approaches 4 from the right, well, looks like I'm headed upwards towards positive infinity, because if I hop on to the right of 4 and heads toward 4, that graph is going up, 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 up. As I head towards 4 from the left, I'm going down, 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 or towards negative infinity. We don't have a value at f equals 4. That graph is undefined, so does not exist. As we head towards the right end of the graph, our y values are going to approach that asymptote at y equals 0. And I thought I was done, but as I scroll downwards now, I see the value, the limit of our function as x approaches 4. Well, from the right, we had a positive infinity. From the left, we have a negative infinity. Those guys don't match up, and therefore that's a DNE. And as far as the value of our function at x equals -1, well, my function, or sorry, this function at x equals -1 has a hole. What that tells us is that there is no output for an input of x equals -1. All right, so you've got some graphs to draw on pages 10 through 13 for homework. And actually, page 13 isn't even a graph to draw, it's just some functions to evaluate. But your homework is going to be pages 10 through 13. Looks like this video is a pretty short video, so you've got lots of time to do it. Of course, if you have questions, please feel free to reach out and get in touch. Cannot wait to see you again. But until then, be well, and we will see each other when we see each other. Take care for now.